Good morning. This is Deep Generative Models, and I am Cheng Wei. Welcome to this class. Today, we are going to talk about some basic information of this class, and I'm going to talk about what the deep generative models are about. So first of all, I'll give you some basic information about this class. So about the course website. So we have an official course website, which is on E3 system. E3 is the official system, course system of National Yangming Jiaotong University. So we're going to use it, and we'll do post the announcement on E3, and also the homeworks on E3. We're going to have like 5 homeworks in this semester, and you can find out the details of the assignment on E3 and submit your works. However, most of our course materials are on a separate website that is maintained by myself on Notion. The URL is pretty simple, very easy to remember. tjwei.tw. TJ is my initials, the initials of my first name, and the Wei is my last name. So tjwei.tw is the website because it is short and easy to remember. So you can either bookmark it, you can just bookmark it, or you can just enter it into the address bar in your browser. So it will redirect to the Notion, and you can see a lot of different items listed on the website. In this particular class, our coursework will be in this one, the Deep Generative Models 2024 Spring. Most of the materials are still taken from the previous iteration of this course, which I believe was taught in 2022. Because this field advanced rapidly, so some of the material kind of outdated, still useful, but we have a lot of advance in these 2 years. So we wish to update into this coursework. So I will update the materials by week, and so for this week, I have already updated the introduction part and the autoencoder part, which we'll cover in this week. So let's go back to the slide, and you will find that there's also a lot of because we taught this course online. So each week we'll provide some lecture videos. The lecture videos will be updated every week, Wednesday, 9 a.m. And the full list of videos can be found on this website, video.tjwi.tw. Again, tjwi.tw is my name and Taiwan, and the first one is obviously the videos, so you can get the whole list of videos. Most of the videos will be published on YouTube. So if you have a YouTube channel, if you have a YouTube subscription or a YouTube account, you probably can find the list and access directly on that. However, if there are any change or any additional, or simply because you find out this URL is much easier, it's easier to remember, feel free to enter this URL into your address bar and find out. You can get all the information you need to access the videos. This course is taught in English because I am not, for some reason I do not fully understand, but most of our course taught in my department are labeled as EMI, which means English as medium of instructions. So it requires that most of the materials are presented in English. I believe there are some benefits because we do have some foreign exchange students, and we probably encourage that people that only speak English can, mostly for foreign students, and can take course in our schools. But also, I believe that most of our students, at least currently, most of our students are still speak more fluently in Mandarin Chinese. So there is also a version of the lecture videos that is presented in Mandarin Chinese will be available if I have enough time to do so. However, the slides itself or lecture note itself will always be presented in English, unless, of course, in some examples that Chinese characters are used as a target, like in training data, or we do believe that in some we will have some examples for the machine translations. So there will be some, potentially there will be some Chinese characters. However, the majority of the materials will be presented in English. The homework, should be remove the space right here. Our homework, we will have a homework approximately every 3 weeks. So each homework is expected to be presented in a format of GP notebook. The homework is going to be straightforward. I won't use the word easy or simple. I would say it is straightforward. Because I don't want to add any pressures in the learning. I believe that the best motivation for learning a thing is some inner motivation or some intrinsic motivations, like you do believe that the materials I'm going to talk about and teach is useful for yourself or for you, for your own good. Not because you are forced to do or forced to learn these things. You have no choice but to learn these things. I believe that in order to learn things better, or then you probably need some intrinsic motivations. So there's no use to add some pressures to it. So and besides, I believe the materials we are teaching are in fact, very useful. You are supposed, I'm expecting that you're already interested in some problems. I mean, some project or some works or some problem you are currently solving or intend to do in the future that will have some use of our materials that is taught in this class. So for example, you want to generate some images, or you try to understand what's happening in this algorithm, or you are trying to find some potential improvement on these algorithms, then you'll find that this course has provide some informations and materials that might be useful for you uh, to do whatever you want to do. So that is that I'm aiming for. So the homeworks, let's go back to the homeworks. The homeworks will be straightforward, not very challenging, because the challenge is in every one you can do something really fancy and really challenge yourself. But the requirement of this homework will be some more of like the baseline or if essential requirement. And there's no such thing as very challenging problem that you doubt yourself that you can, whether you can solve this problem or not. Most of the things are very straightforward. There are going to be some technical challenges like, okay, I do not know how to use PyTorch. I do not know how to install like CUDAs. It takes too long to train these models, such thing as that. But everything should be straightforward. Because if you are learning something, it will make you uncomfortable. It is a side effect or some uh the hint I mean it's the result, the byproduct of learning things. You feel uncomfortable. If you are comfortable on everything, then because you have already know those kind of things, you have already know how to do that. Just like learning a bicycle, riding a bicycle. If you already know how to ride a bicycle, then you will feel very comfortable or satisfying when or enjoyment on riding a bicycle. However, it is totally different for some guy who is currently learning how to ride a bike. You're very unbalanced, strange. Uh, so that's because he's learning. He or she is learning. So that's a sign of learning. So you do kind of feeling something uncomfortable or a little bit challenge, but that's it. There's no something intentional like some trap or some um, trap questions or some difficulty to challenge you, all for the purpose of for fully understand the materials that is taught in the class, to familiar with the things that we have already taught or discussed, or to verify the theories that we have taught covered in this course. Okay, so there are a lot of different topics in generative models, so we can only cover that much. So this is a list, basic list of the topics we're going to cover in this semester. So the first in the first row, there are about some I would consider as a simple or basic part of the generative models, including autoencoders, autoregressive models, and n-gram for the language models. So those are pretty simple, easy. I would say you cannot go wrong with these models. And after that, we're going to talk about the variational autoencoder and again, generative adversarial network. It used to be the major part, in previous course, like 50% or maybe even more are talking about again the generative adversarial networks, because it was a hot topic back then. But after the diffusion models arise, become mainstream, GANs are less important or less frequently talked about in I can see that in the last like 2 years. but we're still talking about it because it is still a very important um, topics and the concept. It just we don't put that much time on it. So there will be like 3 weeks for the generative adversarial networks. Then we're talking about the next 3 weeks. We're talking about the diffusion models. Diffusion models is the current go-to models for generating images or even videos. So we're talking about the series. There are a lot of interesting series about the diffusion models, which some of them are very beautiful. And we also talk about some practical techniques that is currently used in many mainstream algorithms like stable diffusions or in some approaches that use in like imaging, like Google models, images, or similar models. Then we're going to talk about language models, mostly about the large language models, and we're focusing on the generative part, which means we probably won't talk too much about the word to factor or other things. So some of because the large language model is so important and everybody has already used it, maybe a lot. So not only these 3 weeks, you can see that in the first 3 weeks, we are going to we talk about about the n-gram and language models. So we intend to increase the importance about the language models in this and the future version of this course. But currently we are putting it for like 3 weeks. Some of the materials will interact with the module class that I taught last semester, which is a 3 weeks module class. I believe it is a deep language models or language deep learning models like that. Except in this class, we are more focusing on the generative part, not about the things like the word to factor or those non-generative perspective of of this topic. So ChatGPT as a generative model, which will be the focus. GPT models, to be precise, GPT model will be one of the focus of this part, and we're going to talk about relationship between this one and the n-gram generative models. We hope that they can have some connections. And we have a buffer of 2 weeks, which I put it like other method and the recent advance. This is because this field evolved so rapidly. So we almost have no doubt that we are going to encounter some breakthrough during our semesters. So in this case, I can talk about that breakthrough method in one of the in 1 week or two. So for example, currently the most hot trending algorithm is the Sora from OpenAI. The Sora algorithm is so amazing that so jaw-dropping because we can confidently say this is the first video generative model across the line. The line, I mean, people actually believe we can use AI to produce something useful, or just like the DALL-E 2. DALL-E 1 already amazing, but people still think, okay, that's kind of cool, but can it actually do something professional? But after like a mid-journey, stable diffusion DALL-E 2 has appeared. I think currently people have little doubt that the generative models can be used professionally. I mean, in some professional work, or at least help you to do the professional works. For videos, I believe Sora is the first one that people gained really confidence that, okay, we believe one day or even now that generative AI can definitely help or even take over the video generating or video producing industry. So we are expecting some breakthrough like Sora in the future in this semester. So we have 2 more weeks that we can bother to either to talk about more topics like the flow model. Generative flow model is also a very interesting topic, but people doesn't use that much, not as much as like the large language model or diffusion models. And so I can put it into the material, or we, I can have an option that we don't talk about that too. So I have a 2 weeks buffers. I have enough material to put it in there, but I'm expecting that we have some breakthrough advance in the future that we can just cut them into the middle of our semester and talk about that new exciting discovery, which I don't know what it is because it has not yet published, but I'm pretty confident there will be someone right there. There'll be a breakthrough discovery, maybe 2. Okay, so that's pretty much about the how this course are going to work. Let's give some overview about the generative models. I believe most of you have already know what the generative AI or generative model is, but chances are I cannot rule out the chance, the possibility that some people still haven't explored much to these generative models. So for the completeness, I'm still showing some generative some works that is generated by the generative models, so that you can have an idea of what a generative model is. So first of all is the Sora. I have mentioned before, this is the first one that is totally a breakthrough that cross the line of the video generation, I should say. So you can see every video you see on this website. This is the official website of the Sora. So every video you see is generated by AI. So you can see that there's still some Japanese characters that doesn't exist. However, some is very close. And before, like 2 months ago, if I see something like this one, I probably won't suspect this is generated by AI, except for perhaps the strange Japanese characters. Because you can see that the reflection of the sunglasses is so real, and the quality, the skin, the texture of the skin, the imperfection of the skin, and everything, and the consistency. The one of the difficulty of the video generation is consistent. So you can see that, okay, right now I can see that a lot of the Japanese character is definitely generated by AI because they do not exist. However, the consistency is superb. You can see that, okay, the reflection from the water the people, it doesn't, it looks like the same person like the 2 or 3 minutes seconds ago, like 10 seconds ago. And um, you can see there's a scene change, a jump of scene, and still this sign looks exactly the same. So in the previous AI, the consistency is a huge issue. That is why the videos cannot, we can only generate like the 10 or 5 seconds of videos, but not longer. This video is so long that it's impossible. And all, not this is not the only example. You can see a lot of different videos that are generated by Sora. It is so good, almost like it is impossible. If this is not the work of OpenAI, I probably would suspect that it is a fake or using some tricks. It's okay, maybe it is a video to video generation or have some tricks or have some hidden text that we don't know about it. It requires some special condition because this is OpenAI has a lot of amazing works published before. So right now I'm totally convinced that it is the it is what it appears to be, and I already know that it is very close. So I'm actually not surprised by this result. All I was thinking is, okay, when I saw the Sora, the videos, all what I was doing is read it again carefully to make sure I didn't read it wrong, and I didn't surprise. The word did not collapse or uh, I some research may go to cry because okay, I didn't expect this happens, and all their hard work means nothing after this has been published. But I can totally expect to encounter video generating um, algorithm models that is this good in like 1 week or three months or like 3 years. I just don't know when it comes, but I know it is going to come and likely to come in 1 year. If not in 1 year, it should become in 3 years because there are some models that is very close, and I know there are a lot of way to improve it. So I'm kind of expecting some guy doing something like this one sooner or later. It is definitely kind of sooner, but not a lot sooner. Because like 1 or 2 months, I believe like Google released some video models that is all and the stable video diffusion is also really good. So it's just a matter of time or a matter of the uh, hard work of to collecting good quality and the huge amount of data. Huge amount. You only need a huge amount of good quality data. With some, you still need some algorithm to tuning, but it is definitely doable. So for me, it's just okay. I know it crossed the line and crossed the a standard, the making a new bar, and this is a milestone. They have already done it, but not surprising. Just acknowledge it, and you can see the quality of these videos are just so good. Even like the reflection from the mirror, not the mirror, the window, and the consistency. That is all you want to see the quality. So I haven't actually read the details of the 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 blog post and the technique details, but I believe because of the quality, it definitely use some kind of super resolution or uh, kind of like from I believe they do something from the either from a latent space or a lower resolution uh, and iteratively into uh, high quality output, and using some way to do the like attention to cross efficiently do the attention cross all the uh, duration of the videos to make the I think that's kind of some way to overcome the issues of consistency. But I may be very wrong, but uh, I do believe there are some methods to do this, and not beyond the technology that already exists today. So anyway, this is one of the SOTA of like the video or image generation. Okay, and so another example is ChatGPT. So let's go to ChatGPT. I can let's say to draw some image about generative uh, models. So let's see what they can do. And I can actually. So first, I would like the ChatGPT to um, generate some images about some topics. For now, because the name of our course is deep generative model, so I'm asking it to generate some pictures related to this topic, and then I ask him to write a story. So it can generate this text. You can see that chapter one something really amazing, because we are already in a state that the computer can generate very plausible and kind of high quality text materials, which is beyond imagination 10 years ago. Like 5 years ago, we are not sure how soon we can get some quality like this one. But right now, it's just realities. We already got this technology, and everyone has the access of this kind of technologies. So that's actually very amazing. So that is what the generative models can do for you. It can also write not only generate text or videos or images. It can also like generate music, generate programming code for you. Like I can ask him to write a code, Python code, write Python code to generate say all prime numbers under 10,000. So it actually write a Python code to do so. So a lot of people might use the GitHub Copilot when you're writing a code already, and you can already see that it's very helpful and to improve your productivities. Okay, so this is a code which is not bad at all. This is some solid code to find out the prime numbers. Nothing I can complain. So that's pretty much about what the generative models can do for you. So let's go back to time to like 10 years ago, almost or at least almost 10 years ago. These are the pictures, images, uh, some bedroom images that are generated by the first generation of games, the generative adversarial networks. So at least for the bottom ones, these are generated by a DC game. Although you doesn't look much currently in nowadays because we have a lot of we have improved a lot of since then. But back then, this is so amazing. The quality compared to the previous works is uh it's so good. It's so good that the paper and the author present this image. It has to emphasize that these images are generated by AI, not the sample. Because you know that these images are printed on PDF or on in paper. It is kind of small, and it need to be printed in color, so the resolution is not good even for real samples. So if you are not careful enough, and because this kind of things has never happened before, not even close, so people may be very well mistaken these things as a sample, not realize this one of things is generated by algorithm or a model. So this is not good back in 10 years ago. But currently we have improved over this kind of result so much that we have no idea how good this is. We cannot appreciate that this one it was so good and unbelievably good. But other typical, but I'm presenting this as one of the early iconic images that is represents the generative image back then. So other iconic images like the cycle gains and pixel pixel, like this one, when given a sketch of the outline of the images, it can generate this kind of color images. Right now, it doesn't seem much because it can easily do so using the diffusion models and getting much better result. However, it was kind of breakthrough result back to like 7-8 years ago. It was so people didn't think that we can do that. We can generate this kind of good qualities and so easily by just using some simple algorithms. And this one is just from the segmentation. We can generate photorealistic images. And people are very interested in generate human faces. This one is supposed to be some of the achievement back in sometime like, I don't know, 10 years ago, 8 years ago, or 6 years ago. But we have come in a long way. So after like the progressive progressive growing game, our standard is become very high. So this kind of faces are terrible in current standard. But back then, we have work for, we have come from here for a very long road. So this one was once an achievement in the long history of developing the algorithm so far. And the above is some simple example of generating MNIST characters using some. I believe this one is using variational autoencoder. Also, I forgot which one, but this one is something recent that the generative models for like 10 for 5 years. So you can see a lot of articles or like a video interviews or something about the generative models. You can see a lot of pictures, images like this one. The following is one of our work that is generating a font. So not only we generate images, so we can generate images like this one, but the major result is we can generate like a true type of font, a scalable font in this case. So each strokes are different. Not only we generate the outline, we actually generate strokes of the character. So this one is a Chinese character. So the rightmost one is the, you can consider as the ground truth, that is designed by a human designer. And we can see a few examples in the data, and the generator similar for the character. It does not think by models, and it can generate various different type of font. So when you, a new font is given, you can give it like 500 word, and the model can generate the rest of the font. Not perfect, but because the designers are very picky, so they actually can find out the difference between this one and this one. We can find it, but we don't think that is, I mean, from our naive eyes, it doesn't seem like I cannot tell which one is better, but the designer can. There are some way to tell the difference. So for this one, there is not even in the data set because designer haven't. This one is a more rare character, so the designer doesn't even design this character. However, because the model can generate something that it can haven't seen before, so we can generate some missing characters in this form. So this is something that the generative models can do, and this is like I don't know 5 years ago. So currently we have much more tools like large language models, diffusion models. So in fact, there are many ways to do this and can do much better. So these are a few examples back in like 3, 4, 5 years ago on like generate videos over the, okay, I don't want to put it, I'll make the sound because the sound is very annoying. But we can actually generate some videos using different text prompt to generate different person in a video. And this one maybe like 1 or 2 years ago. Now we can generate something like a person that is doing some actions. So, but currently, we use a lot of different tricks. But just as we predict back then, the tricks will soon be rendered useless because some general and powerful method will be invented in very, very soon, not more than 3 years, perhaps in 1 year. That is what we predict like 1 or 2 years ago. And it actually happens right now because the Sora already did what we anticipated that will come in really soon. Okay, so those are just a few examples that give you an idea of what generative models should be or is. But really, what is a generative model? So let's go back to some, what is so special about generative models among the machine learning models or deep learning models? So one of the typical machine learning, or arguably might be the easier task of machine learning is the supervised learning models or algorithms. So a typical one is, or the entry level tutorial one is the MNIST. MNIST is a data set that contains a lot of handwritten digits. Digit by digit, I mean the 0, 1, 2, 3, and to the 9. We have 10 digits. So for each image, 28 by 28 grayscale image, we have a digit. As you can see that we have a 5041 in the near about the top of these images. So for each images, we can kind of making it like a vector. We convert the we can represent the grayscale into a number And because it has a 28 by 28, each pixel corresponded to one number. So we can easily convert this image into a vector, into a vector. So after it becomes a vector, we can use a lot of different numerical algorithms to process it, to do the machine learning we want. Specifically, we are using currently mostly I'm talking about using the neural network to do so. A typical way to using a neural network to do the handwritten digit recognition is as following. So first, just we said before, we convert the image into a vector. So we are converted the image into a vector. Then we can feed it into a neural network. So because it is 28 by 28, so the input dimension is 784. That is 28 times 28. So we make these images into a vector of 784 components. And then we feed it into a neural networks, and we design it to output like 10 numbers to represent the probabilities of the models consider the this image, the digit that is corresponding to these images. So for this image, the digit corresponding to it should be 1. For the list 4, like it should be 5041. Okay, for this one is 1. So the output, there are 10 outputs. The 10 outputs are corresponding to the probabilities the model consider this image to be the corresponding digits. For example, in this output, we interpret the output as this model think this image have a 0.01 probability. Let me silent this phone. It's just too annoying. I don't know how to do that. I already put it in the list follow. Okay, so this one is 0.01. The probability of this one being 0 because we start from the digits start from 0, 0, 1, 2, 3, and to 9. So it consider this image to be 0. The probability to be 0 is 0.01. That is 1%, which is very little. And consider it has 80% probability to be 1, and 1% probability to be 2, and 2% probability to be 3, and 5% probability to be 9. So that's it. We input the input is a vector, and the output is also a vector that represents a probability. So after that, after the model has already designed, we can feed the model using like a gradient descent algorithm, a machine learning algorithm to optimize the model, the weight of the models. So there are a lot of different weight. Each weight is assigned to an edge, an arrow on this one, which we can change the weight to something optimize the result that we are hoping the model to output. So for example, if this one is the input, we want this one to have the maximum probability on the output that corresponding to the digit 5. And for this one is 0, we wish this one to be the maximum, to be the largest one among all these 10 outputs, and so on. So by using the training data, we have like 60,000 training data. These 60,000 training data, each sample has a pair of image and its corresponding digits. So we also usually call the input image as X and the output digit as Y. So we have the ground truth Y and the input image X. So by using the training data to do the training, we can find the optimal weight of this neural network, and hopefully it can generalize well on images that have never seen by the model. It's not in the training data, and still do the recognition. And neural network is surprisingly good at generalization. Although we often consider overfitting is a major issue of the machine learning, but neural network is in general kind of good at generalization. So um, so at least for MNIST, if we're training the model on the training data, it can actually perform pretty well on the testing data. So this is a general supervised learning setting. So basically, we want to find a function, or this function is there has some weight to define this function. And given input here, we wish it to output the corresponding digit that represent in that is drawing on this image. So what is the generative models? Generative models is kind of okay. I forgot to remove this one. This means the generative models, because I modified the slides from the previous one. So this one should be in English. Okay, so for generative models, when we get an input of a digit, we want to kind of do the reverse. When we take an image, digit right here, we want to output the image. So what is the difference between the, maybe I think this one is a major mistake. I probably shouldn't. Okay. 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 So you can see the difference between this one and this one. So what is exactly the the difference between generative model and the usual let's say the supervised learning? You may see like, okay, they are reversed because one is taking a number as output and the image as an input. But in a generative model, we take a number, a digit as an input and the image as an output. But if you really think about it, the image is a vector, just like we said, we convert it into a vector. And also the output is also a vector. They have different lengths. One is 784, but the other is a length of 10. This vector is length of 10. But nevertheless, they are all vectors. They are just vectors. There's no difference. Mathematically, they are just vectors. So no matter this one or this one, we are constructing a function that taking a vector as an input and the other vector as an output. And for the training data, we already have the pair of x, y. In the generative model, we simply just exchange the y to as an x and the x as a y. We still are doing something kind of like the supervised learning, except we're kind of using the training data more creatively, by exchanging x as y, y as x. But fundamentally, they are still the same thing. We just exchange a row, so that the input is a little bit smaller and output is a little larger. The dimension. But fundamentally, essentially, they are just a simple thing. So why do we even bother to consider this as a different category of a problem? So there are some major difference right here. So one is the structure prediction. So because the in generative models, one thing is very important, that is our generative things are more structured. For example, you can see the image right here. This is a real image from the Science Museum of Minnesota. So we can definitely see this one is not a real human face. For every part, for every single small part, local region, they are very realistic because they are real images taken from the real human beings. However, they does not collect them together. It does not doing very well because no human being looks like this one. Maybe I mean people have some sunburns. Some parts a little bit darker than the others, but it definitely doesn't look like this one. So not only we want to generate everything, if we want to generate an image, not only do we want to generate every pixel perfectly, the pixel and the pixel has some correlation between each of the pixel in the images. So we cannot kind of like doing something like a divide and conquer strategy to do so. If if we can generate each pixel perfectly, then we can combine all these pixels together to construct a perfect image. If we can do something like divide and conquer, then we can do something like that. However, in this case, we cannot do so. So we are encounter a very difficult and complicated distribution. Not some IID. When I say IID, this is means the uh, independent identical distribution. This is a general design. General assumption in many questions in the probabilistic and the statistical uh, issues. For example, if we flip a coin, we assume that the coin have the same property, maintain the same property of the head and tail in each round we throw it. They keep the same. So that means identical. And the first row and the second row, they are independent result. That means independent. So IID means that kind of settings. But obviously, um, if a problem has an IID, we can kind of divide and conquer the whole thing because we can deal with one coin flip at one time. However, when we want to generate an image or an article, a paragraph of text, it usually that each part of the generated things, the stuff has correlated with other part. So that make the probabilistic distribution of that kind of target very complicated because the correlation between each pixel is important and significant. Not only the correlation between two pixels, maybe 2 or 3 pixels or 4 pixels, you cannot stop just right there. You have to consider the correlation between every pixel and all other pixels. So you need to consider the whole pictures, the whole joint distributions. So that makes the distributions really difficult. And another thing is that you need to consider the probability. The another major difference between this guy and this guy is when we see an image, we are certain the result. There are just only one result, and every time I give you this image, I'm expected that you generate the same result. If the input image is 4, you will output 4. Next time, or most of the time, you should have to generate the same numbers, at least for the correct answer. If you are trying to doing it funny or doing it wrong, you can generate whatever you want, but the correct answer should be expected to be the same every time. However, in this case, what we are thinking is we wish it to generate different image every time. So that is significant and essentially fundamentally make the problem more difficult. That is, we have to deal with the probabilities, kind of related to this one. because everything goes to the probabilistic distribution. So imagine that we get rid of the uh, probabilistic part of this question. If we give you a number, you simply generate one image, and you can generate the same image over and over again. Then this problem becomes so easy that you don't need like 60,000 training data. You only need 10 training data, and the only requirement is this 10 images from the training data comes from different part of the digit. They have the different digits for each of the images. For each of the image, they have distinct digits. Then, if I want to generate a 5, I simply find out the images corresponding to 5 in these 10 images and copy it right here. For 4, I find the 4 image and copy it right here. And for 1, I find the image of 1 and copy it right here. You can see that it's not even a machine learning problem anymore. It is so easy that it can be done by a simple algorithm. So you can see that the probability part is crucial in the problem of generative models. If there are no anything involved with probabilistic nature, then probably this one can be considered as a supervised learning because it is so easy. So the probability the part is probably one of the root of the difficulty of generative models. And usually the probability is going to be very complicated because there usually has some kind of very complicated structure between all the dimensions, all the pixels, all the tokens in a text generation. So the probability, not only it has a probability involved with the problem, the probability is usually very complicated. Okay, so I should fix this one. Okay, so let's back to the problem itself. So a generative model is basically the problem is when we are given some examples, then we wish to find out or construct or mimic the distribution. So by given those examples, we want to construct a new model that can randomly generate some samples, and hopefully these two samples are similar. So what does it mean by similar? In mathematics speaking, the standard way to say that the samples and your models are similar is measured by the likelihood, which means so this is your model. This is your model. Your model can compute the probability of this sample, the probability, the density of this sample. So if you can compute the density of this sample, because we are consider the samples come from an IID, independent identical distribution. So the whole density, the joint density can be multiplied them together. So all we need to do is find a weight, a theta, so that the sample that we are seeing is most likely to appear. So among all the possible thetas, we find out the maxima, the theta that maximize this formula. You can consider this as just simply the joint density. However, because it is usually easier to do the summation than do the multiplication. So if we take the log doesn't change the order of the things. So we can still maximize this guy. And by taking a log, the log when we exchange the log and the multiplication, it becomes the summation. So it will be easier to compute than we use the origin form. So that's why we often use the term log likelihood, because it is pretty straightforward, very intuitive, and easy to compute. So all we need to do is to find a theta. So the sample that we observed is most likely to be get or observed in the model itself. If we consider the samples, we can kind of approximate the samples into a distribution, or imagine there is ideal, theoretically imagine there's a distribution corresponding with the samples. Then we can compute the distance between the model and the model distribution and the real distribution using various measurement of the distance between, or the divergence between the distributions. There are a lot of them, like Taylor divergence, Jensen-Shannon divergence, and other. Because the density function is just a function, so any measurements between two functions can be used to compare with the similarity between two different distributions. So Taylor divergence, Jensen divergence can be used like that. So there are actually some ways to measure the difference between models, distributions. So that's what we use there, theoretically. So in the history, there are some usage of the terminology of a generative model. One usage is from the statistical classification. You can see it from the Wikipedia. So in some definition, generative model is some models considering with the joint distribution. This is mostly in the context of classification models, but with different approach. So one approach is using the joint distribution of the x and the y, the input and output, the input and the ground truth prediction, the label. I mean the label. And discriminative models are other models are called discriminative models. One of the most important case is that given x and we find the property of y. This is pretty much the abstraction of the models that we gave before, like this one. I mean this one. This one is y. The property of y, the capital Y is just this guy, and we are giving x is equal to this guy, the small case, the little case x right here. So this one is exactly the same thing right here. So this kind of model is called discriminative models. Some kind of model doesn't even need any distributions. So this is also called discriminative models. So for example, the generative models are some naive Bayes classifier, or LDA, linear discriminant analysis. And the typical discriminant models are logistic regression. It can be generalized to be, a neural network can be considered as a generalization of a logistic regression. So pretty much a standard, those two are standard ones of the discriminative models. However, do not consider this as a standard. So this is just one opinion, or some kind of usage in some certain field, because generative model is a so common word, so it may comes from a lot of different areas, I may imagine. But in this field, statistical classification, in this field, and some scholars believe this definition. So if it is very possible some guy use this the very similar um, terminology, but refers to something slightly different or maybe a lot of different than this definition. So do not ask people to identify. Uh, if somebody use something like a generative model, do not identify. Ask people to identify. Okay, you to call this a generative model. What is your PXY? Do not use that because this is just an opinion. So the terminology varies in situation, in context. People are very casual to using this, usually very casual to using this terminology. So chances are they are not in the same, we are not talking about in the same context. So treat this terminology as a casual meaning. Do not always stick to the most strict definition. It will make you like a jerk. Because even in the same statistic classification, the field, some people comes up with a different definition, like this one. The discriminative model is pretty much the same. Given x, you'll find a y. However, when talking about the generative model, it kind of exchange the x and y right here. Kind of like what we did right here. And here, that the different, this one is exactly the same definition. And this one is more like the structure. What do we call the structure? Predict like the structural things, like we call the we say that we need some joint distribution because the structural prediction is needed. There are a lot of correlation between all of the things. So both of this definition captures some important characteristic of the generative models. But in my opinion, most of the case, people are talking about these terms. Generative models, distributed models are more in a relaxed and casual context. Just like we are talking about supervised learning or unsupervised learning. Do not ask them the strict definition because there probably no one. There's no one exists. Okay, so there are a lot of different generative models right there in different contexts, in different algorithm. I didn't list the diffusion model and again right here because we're going to talk about them in our class. So I'm just listing in a lot of things here just because I know I cannot cover everything. So let's go back to the scope right here. These are the models that we're going to talk. You can see that the time duration is a little bit different than the one before because like I said, I kind of modified them a little bit. Okay, this one are the same. The 3 1. Okay, this one that's still the same. But anyway, this is subject to change. Depends on the situation. I may make a little bit the motivation here and there. That is expected. Okay, that's pretty much of it. So in the next video, we're going to talk about autoencoders. So see you next one.